All right, you're all set to start, Dr. Chua.
Okay, so thank you all for coming. I'd like to introduce Dr. Edward Norton, who's a professor in both the Department of Health Management and Policy and in the Department of Economics at UM. He's also a member of IHPI. In addition to his affiliations with UM, he is a research associate at the National Bureau of Economic Research in the economics of health and the economics of aging programs. His research interests in health economics include econometrics, long-term care, and aging, and pay for performance. He was the director of the RWJ Foundation Scholars in Health Policy Research at UM. And before coming to UM, he was at the UNC at Chapel Hill and at Harvard Medical School. In 2018, he won the School of Public Health Excellence in Research Award at the University of Michigan. Today, he's going to talk to us about log odds and ends, marginal effects in Logit models. Thank you very much. Thank you for Dr. Norton for coming.
Okay. Thank you. Thank you very much for inviting me. This is a topic that I find really interesting and important, given the number of papers that use odds ratios. So primarily, I'm going to talk about odds ratios. Next slide. Okay. So there are many ways to express the strength of association between some outcome and risk factors. We can express them in terms of probabilities, odds or odds ratios, their risk ratios, risk differences, marginal effects. And so my goal today is to try and provide some insight into the interpretation of odds ratios and their limitations and some alternatives. I'm mostly going to talk about odds ratios. Next slide. Okay. So I think, given what I know about this audience, a lot of what I'm going to talk about at the beginning is going to be very much review and very basic, but hopefully by the end I'll have talked about things that will be new and different. So I want to start with the absolute basics and then build from that. So the odds are the ratio of the probability that the outcome does occur to the probability that it does not occur, often written as P divided by 1 minus P. So for example, if the probability of going to a hospital in a year is 20%, then the odds of that would be 0.2 divided by 0.8 or 0.25. You could also express that as the probability of not going to the hospital. And then the odds of that would be 0.8 divided by 0.2 or 4. Okay, so odds can obviously be not only positive, but above 1. Next slide. If the probability is really small, then the denominator is very close to 1. And basically then the probability is the same as the odds, approximately true. But as the probability grows, then odds and probabilities diverge. The wonderfully oxymoronic phrase, even odds, means when the odds are 1, and that would be when the ratio is 1, or the probability is a half. Half divided by half is 1. And odds, of course, can never be negative, but there is no upper bound. Next slide. Odds are used by gamblers. So if you're a degenerate gambler, this slide is old hat for you. The probability of picking a card from a standard deck of 52 cards, and if you think about the probability of selecting a spade, that would be 1/4, right? So the odds of selecting a spade would be 13 divided by 39, or 1 to 3. And one way to think of it is if you bet $1 on the probability of randomly selecting a spade from a fair deck, then you need a payoff of $3 to break even on average. Okay, so 1 to 3, that's where that comes from. All right, next slide. All right, so what I've talked about so far is just single probabilities, no covariates, but we want to go to a world where we can now correct for various covariates. And so we'll go to logistic regression. We have an outcome which we express as either 0 or 1, and use the logistic function to make that probability a function of a whole bunch of x's. So x prime beta is shorthand for having an intercept, and then as many covariates as you want. These could be continuous, they could be binary, and each covariate has its own beta. And so we want to think about how to interpret the beta on these coefficients. Now, the logistic function is really nice because, unlike ordinary least squares, this is going to, by definition, bound this function in between 0 and 1. This can never get bigger than 1, and it can never get less than 0. Okay. If x beta gets really big, e to the minus big number gets very close to 0. 1 over essentially 1 is 1. When this gets very negative, this gets enormous, and this whole thing then goes to essentially 0. It's bounded between 0 and 1, which is very nice because you can never get negative probabilities. You can never get probabilities that are greater than 1. Okay, moving on. We want to get back to thinking about beta. Next slide, please. So how do we think about betas? Beta on its own is not a probability. It can be negative, it can be big, positive. Nor is it directly an odds ratio. It's what we call the log odds. So one way to think about that is the odds ratio is the exponentiated beta, or if you take the natural log of this, then beta is the log of the odds. So to go back and forth, it's exponentiation or natural log. Just a few examples here. If beta is 0.4, then e to the 0.4 is about 1.5. If beta is 0, then the odds ratio is 1. So this is the even odds case. Beta of 0, if you have no covariates and this is just a constant, then beta of 0 indicates the overall probability is 1/2. If beta is, say, minus 0.2, then the odds ratio is just over 0.82. And if beta is small, very close to 0, then the odds ratio is very close to 1 plus beta. And again, as that diverges from 0, then that approximation gets less good. Okay, so let's move on. One way to think about this is comparing two groups. You could think of smokers and non-smokers, treatment versus control, someone with diabetes versus someone without diabetes. Think of a binary variable. And then you can write down an expression for the odds of one group, say treatment, versus the odds of control. And that would be the probability for, say, the treatment group divided by 1 minus the probability for the treatment, all divided by the probability for the control group divided by 1 minus the probability for the control group. Lots of probabilities, lots of division. And the general idea here is that the odds ratio for a particular risk factor is indicates whether someone with that risk factor is more or less likely than someone without the risk factor to have the outcome. So if we have treatment versus control, and the odds ratio, after doing all this math, is say 1.2, that would indicate that someone in the treatment group is more likely to have the outcome. If it's right around 1, then it's about even. If it's less than 1, then the group in the numerator is less likely. Okay, next slide. Let's do a specific example with some real numbers. There was an article in JAMA 2017 by Tringale et al. They looked at industry payments to physicians. So do physicians not only earn income by seeing patients, but also do they get some sort of industry payments? Yes or no? It's not about the amount, just do they get payments? And overall, just over half of men received an industry payment. Over 40% of women received an industry payment. So we can take these two simple probabilities, no adjustments yet for covariates, and just plug them into our formulas. The odds for men, this is just over 50%, so the odds are going to be just over 1. The odds for women are less than 1, so 0.426 divided by 1 minus that. The odds ratio, men compared to women, is the ratio of those two numbers. So it's about 1.4. You could also do odds ratio of women to men, other groups. But this says that the odds that men receive industry payment is about 40% higher for men than for women. Okay. All right, next slide. But that very simple analysis didn't control for any covariates. It could be that men and women are different specialties. Maybe different specialties have different probabilities of receiving industry payments. So they did a logistic regression controlling for lots of things, and that odds ratio was then reduced after controlling for other things to 1.28. Okay, so a little bit more precise. Next slide. All right, so now I'm going to talk about two problems with odds ratio. The first one is well known, and the second one is less well known and more interesting. But the first one is just lay audiences tend to confuse odds with probabilities and tend to say one when they mean the other. We know they're not probabilities, but sometimes people confuse them. Odds ratios are also not risk ratios. When the probabilities are very close to zero, doesn't matter a lot. But as they diverge, then this can be much more confusing. This is a well-known problem, nothing new, and it's basically an issue of education and being very clear and explaining things, okay? And if this were the only problem, I wouldn't be giving this talk this morning. Next slide. So another interesting thing about odds ratios, if I just tell you, say that the odds ratio is 2, say comparing men to women for some outcome. That would be true if the probability for men was about 1% and for women was 0.5%. So two very small numbers, ratio of 2 to 1. But that's also true for 50% for men, 33% for women, or 80% for men, 67% for women. This shows that when talking about odds ratios, or actually risk ratios or marginal effects or anything else, it's really important to show the underlying probability as well. A single statistic is usually not sufficient to convey fully what the study is about. So you'd want to say, odds ratio is 2 and the underlying probabilities are something like this. All right, next slide. All right, now things are going to get more interesting, I hope. This is the second problem with odds ratios, and that the odds ratios are scaled by an arbitrary factor. And the scaling factor is the square root of the variance of the unexplained part of the binary outcome. And I'm going to come back and explain this more carefully with intuition from ordinary least squares regression. And for those of you who are more mathematically inclined and want to know more about this, you can see the full derivation in this health services research paper with Brian Dowd for 2018. Okay, next slide. So I'm going to give a metaphor here for why odds ratios are confusing. And imagine that there's a website selling something, they list prices, but they don't list the currency. So is it in dollars? Well, you might infer that if it's an American company, but maybe it's in pounds or euros or yuan or some other currency unspecified. Price is just 20. Do you want to buy it? Maybe it's in Bitcoin. Right, so then it's really fluctuating. This is going to be, that's the metaphor I want you to keep in mind when we're talking about odds ratios. You don't know the currency after running a logistic regression. Okay, next. So let's go back to the scaling factor. The scaling factor is going to change when variables are added or eliminated from a logistic regression. When you add variables to a logistic regression, you explain more of the original variation in the dependent variable, the same as you do for ordinary least squares regression. If you add more variables, unless there is completely unrelated to the outcome, they will soak up some of the variation, leaving less unexplained. And it turns out, and I'll show you how this works in a moment, that when you add variables and they explain part of the variation in the dependent variable, that'll end up increasing the odds ratios, even if those variables are independent of the other variables in the model. Okay, so everything I talk about here is going to be adding and subtracting variables that are completely independent of everything else in the model. If that's not true, then we have an endogeneity problem. That's a different issue on top of what I'm talking about here. So let's just think of adding variables that are uncorrelated with each other. That makes things nice and keeps the point on point. All right, next slide. So the consequences of having this arbitrary scaling is that there is no one unique odds ratio for whatever research question you have. Okay, so it doesn't make any sense to talk about the odds ratio. There is no the odds ratio. You estimate an odds ratio conditional on your sample and on the model that you estimate. Okay, that's very important. And because of that, you cannot compare odds ratios from the same study using different model specifications. They're not comparable anymore. It's like different currencies. Nor can you compare an odds ratio from one study to another study, that is using different data sets. I have a, Medicaid data set, you have a Medicare data set. We run same model with same variables. Our odds ratios cannot be directly compared in magnitude. Okay. And we cannot use the standard robustness checks to see if the estimated coefficients are stable. That is adding more variables to see if things are stable. All right, next slide. Let's go back to ordinary least squares regression. One of the, I teach linear and nonlinear econometrics, and one of the standard themes is let's start with OLS, make sure we understand what's going on there, and then see how our intuition fails in nonlinear models. And this happens over and over again. So let's go back to OLS and understand what's going on in this context, and then see how things break down in logistic regression. So let's say we have a continuous variable y star, and it depends on a few covariates. And of course, there's an error term, and the variance of this error term we'll call sigma squared. So that's the unexplained part. And when sigma squared is big, your R squared is small. Sigma squared is relatively small, your R squared is big. But that's the unexplained part. If you have no covariates and just a constant term, then sigma squared is the variance of the original variable. As you add more variables, sigma squared gets smaller. Okay. If you add more variables, and if those variables are independent of all the other variables that are already in the model, then what happens? Well, one thing is these betas stay exactly the same. Okay, if I add new variables that are uncorrelated, independent of all the other variables, these betas will stay the same. I just add in new variables. And the second thing is sigma squared goes down. Okay, so those are two things to remember from ordinary least squares regression. Next slide. Now let's go from OLS to Logit and see what changes. Now we don't have a continuous variable anymore. We're going to shift from y star to y, which is either 0 or 1, depending on whether y star is above or below some threshold. Could be 0, could be 1,500 grams for low birth weight. Depends on my context here. Okay, so next slide. So Now we want to write a precise statement about the probability that y is bigger than t, which is like, what's the probability that y star is bigger than t is like y being 1 as opposed to y equals 0. Okay. So the probability that y star is bigger than the threshold is the probability that this expression, x beta plus epsilon, is bigger than t. That's from the original OLS model. Rearranging, that's the probability that the error term is bigger than t minus x prime beta, or flipping things around due to symmetry, we can say the probability that the error is less than this amount. Now the threshold here we can absorb into the constant term, doesn't really matter. The probability that a particular value, the error term, is less than a particular quantity is a nice standard statistical thing. This is a well-defined probability. If we give a distribution to the error term, then this becomes a cumulative distribution function. So if we assume a distribution for the error term, then we can write a precise statement about that. And the other thing is this error term has to be what's called a standardized, meaning mean 0, variance 1. Mean 0 is not an issue, that gets absorbed into the constant term, but the variance of 1 is important. Okay. We have an error term that's standardized. We can make very precise statements about the probability that the error, like a normal error term, half the time it's negative, half the time it's positive. The probability of being a standardized normal variable of being bigger than 1.96 is 2.5%, things like that. So, okay, this is all like standard statistics, right? So we've written down a statement from our original OLS, we've pushed things around. Now we're going to standardize things. This is what always happens. So that sounds innocuous. What could possibly go wrong? And my kids have learned whenever I say what could possibly go wrong in the middle of a story, that's when to really pay attention, because things are about to blow up and there'll be flames and things hitting the fan and all that. So that's what's about to happen on the next slide. Okay, so we can drop t because that gets absorbed in the constant term. The typical assumption here in statistics is, well, let's let sigma equals 1. It's normalization, it doesn't really matter. Let's move on. Let's not do that today. Let's leave sigma in. See what happens. So probability that y star is bigger than t, that's going to be the same as the probability that y equals 1. It's the probability that this is less than this, t has disappeared. We're normalizing this by sigma. And if we assume a logistic distribution, we can write it with the logistic function. So this hopefully looks familiar, 1 over 1 plus e to the minus x beta over sigma. And we're going to leave sigma in from now on. That's going to be important. Okay. So hopefully this mostly looks familiar, although at this point in textbooks, sigma often disappears. We're not going to do that. Next slide. Okay. So going back to the original simple formula, odds are p over 1 minus p. Let's write down how that works with this kind of expression. And we're going to write this in terms not only of beta, but beta and sigma. And sigma is not going to fall out of this conveniently. The logistic function is nice in many ways. Things fall out in a lot of cases, but not now. There is a typo in the HSR paper. There's a minus sign here, which shouldn't be there. But if you write p over 1 minus p using the formula from the previous page, you can get this, and then things simplify, and you end up with just e to the x beta over sigma. Okay. But sigma is still here. So that's the odds are e to the x beta over sigma. All right, next. We can also show a particular example about odds ratios. Again, let's do this for smokers versus non-smokers. Odds for a smoker are the expression from the previous page where we have a dummy for smoking versus non-smoking and other stuff. Odds for non-smoker are similar, except they're a non-smoker, so this term falls out. If you take the ratio, wonderful mathematics of exponents, almost everything falls out. The only thing that's left after dividing things out is e to the beta on the smoking variable, but divided by sigma, okay? So the log odds in this case, smokers compared to non-smokers, are the beta on the smoking dummy variable divided by sigma, okay? Next slide. All right, but what is sigma? Yeah, it's the standard deviation of the error term, but sigma is unknown. We don't know what it is. It fell out of the model. And there are a couple ways to think about this. One is that whether or not y star is above or below the threshold, once you take a continuous variable and just say, are you above or below the threshold, the units don't matter anymore. So you could have a threshold for a very low birth weight baby of 1,500 grams, or you could express it in pounds, which is what, 4 pounds, something like that, a small number of pounds. Or you could express it in stones. That's another unit of weight measurement. It doesn't really matter what the original units were. Once you dichotomize it, that's all irrelevant. Sigma is really relevant when you have a continuous variable. And so one way to think of this is, well, sigma doesn't matter because we don't have a continuous variable anymore. Sigma is tied specifically to the units of the original continuous variable. We don't have a continuous variable, who cares? It does matter though. Next slide. Because it's a measure of this unexplained variation, when we add variables to the model, sigma will go down, just like in OLS. And when sigma goes down, beta over sigma goes up. And so what's going to happen is that beta over sigma will typically change as you add variables or eliminate variables from a model, but by an unknown amount. In other words, the sigma part of that is the unknown amount. Okay, next slide. So again, there is no V odds ratio. There's no single odds ratio. It is conditional on the sample, the data set you have, and the model that you run. And so it just doesn't make sense to talk about V odds ratio. An odds ratio does indicate the sign above 1 or less than 1, and whether one group is more or less likely to have the outcome. But that's also true for the original beta. I hear people talk about, well, run a logistic regression, get a bunch of coefficients. I have no idea what they mean. All they indicate is like sign and some sense of unknown magnitude. I want to put it in odds ratios. Well, I would say exactly the same for an odds ratio. Okay. Next slide. So as I said before, if you estimate an odds ratio with a different model specification with the same data set, the odds ratios are not directly comparable because they have different sigmas. You should get different numbers, odds ratios, when you change the variables. And similarly, if we have two different data sets, you cannot directly compare them because they're specific to that data set and that model. And two papers have made this point very clearly before. Okay, next slide. One way of showing robustness with ordinary least squares is to run a simple model and then throw in patient characteristics and then throw in lots of covariates for health status, and then throw in hospital fixed effects, and then throw in more and more and more control variables. And to see if whatever your main comparison is, whether that remains stable after controlling for lots of other stuff, that may indicate some robustness. Often things move around. That makes absolutely no sense with a logistic regression, because even if beta is stable, beta over sigma won't be. And you're estimating beta over sigma, and you have no idea what sigma is. So you don't expect it to be constant. Okay, next slide. So these implications are not yet widely appreciated, and papers frequently report odds ratios as if it was some absolute number that you're trying to find, like pi or some other constant, universal constant, without explicitly conditioning on the model and the covariance. Okay. Next slide. So on the other hand, it's also completely incorrect to say that odds ratios have no meaning. I would say exactly the opposite. They have an incredibly precise meaning, a very narrow meaning. That is that odds ratio applies to that data set and that model, but no other. So in other words, the magnitude is not generalizable beyond that particular regression and data set. Okay. So it's absolutely got meaning. It's a very precise meaning. Next slide. Okay. Let me try and provide some more intuition for why the odds ratio changes. I've given one metaphor, which is OLS. And let me try and give another one, which is, suppose you're trying to test the probability of testing positive for COVID as a function of being vaccinated and perhaps other variables. And of course, there's lots of things that affect whether or not people test positive for COVID or not only being vaccinated, there are many other things. And what you really want to know is for identical people or otherwise identical people, one who happens to be vaccinated and another not, what is the effect of the vaccination on the probability of getting COVID? We could start with the entire world population of almost 8 billion people. But suppose you could collect data from the data fairy, who gobs of data. There are a lot of reasons why various people do or do not test positive for COVID, right? You have hermits living alone, no contact with other people, they're not going to get it. You have other people who are in contact with people as local epidemics blow up, and they're very likely to get it. Contact with others, vaccination, other exposure, et cetera. There are lots and lots and lots of reasons beyond the one thing of, did you get vaccinated or not? As you add controls, you go from an original regression, or logistic regression, which is just, I'm going to control for whether you're vaccinated, but I don't have controls for all the other things that could be going on. As you add controls, you help explain away for some people why they are or are not getting COVID. And one way to think about it is you're reducing your sample to a set of people who are very, very similar to more and more similar to each other. And for whom the only thing left to explain positive test for COVID or negative test for COVID, the only thing left is whether or not they're vaccinated. As you explain away everything else that's going on, soaking up all that variation, you're left with a group of people for whom it's the vaccination that actually matters. And so with the original data set, being vaccinated or not is one of the huge number of factors that could explain it. It's going to have a very small explanation. As you put in controls and highly predict other people and why they are or not getting COVID, then you're left with only one thing that can move the needle. And that's going to make the effect of vaccination on the remaining sample big. Because that's going to be the one remaining factor after you've explained away where they live, how many people they come in contact with, whether or not there was an outbreak of COVID near them recently, et cetera, et cetera. If you remove all these other explanations, you're left with the vaccination being the only thing that can explain it. And that for the remaining population is going to have a huge effect. Okay, so you would expect beta over sigma then to get bigger as you narrow the sample down to people, to identical twins for whom vaccination is the only possible explanation of whether or not they're testing positive. Okay. All right. Next slide. It's also not the case that you should never, ever report odds ratios. They come out of a long history in epidemiology where they're absolutely appropriate and the right thing to do, and not reporting odds ratios in those cases would be irresponsible, because for case-controlled studies, that is the only correct interpretation. I don't have time to go into that. For economists, it's Chamberlain fixed effect Logit model. But if you have basically paired subjects, one of whom's a smoker, one of whom not, one has treatment, the other is control, and they're alike in all other ways, mathematically, you've kind of wiped out the, you no longer have a fully representative sample, and so you don't have an overall probability that's representative of the real sample anymore. All you have is a relative effect of the treatment versus control, and odds ratios are absolutely the right thing to do. Okay. But unfortunately, that appropriate use in epidemiology just sort of expanded to other cases where you don't have case control studies, and then it's no longer appropriate. Next slide, please. Okay, so instead of odds ratios, I much prefer marginal effects or risk differences, combined with saying what the underlying probability is to provide context. So this would be a percentage point change. Now you should immediately ask, well, marginal effects in Logit, how do you calculate those? Well, it's actually the beta over sigma times p times 1 minus p mathematically. It depends on beta over sigma. And you say, aha, that formula depends on beta over sigma for the marginal effect. That number is going to be messed up too. Turns out it's not messed up. Marginal effects are stable as you add or subtract covariates, because it's beta over sigma times p times 1 minus p, and the p's change also in an interesting way that all adjusts. So marginal effects are not sensitive to changes in sigma. And therefore, you should use marginal effects whenever possible. So there's a JAMA paper that talks about that also. It's also in the original health services research paper. Let me go to a quick example. So this is made up data, and they're going to show what happens when you add additional independent variables to a model. The odds ratios are going to increase and the marginal effects will stay the same. So this is from the health services research paper. Next slide. All right. So what we have are 4 different regressions. The first 2 are a linear probability model, that is ordinary least squares. And XD is a dummy variable, X1, 2 are continuous variables, X3 and X4 are additional continuous variables that are independent of these. So the simple model has this dummy variable, a couple of continuous variables. And then if you throw in additional variables that are unrelated to these, you'll see that the R squared in this case goes from 0.2 to about 0.6. So we're explaining a lot more of the variation. But these betas remain the same. Essentially the same. These are not moving. So we add new variables, R squared goes up. These betas are holding constant. Okay, it's exactly what you would expect in ordinary least squares, even with a binary outcome. Here we have a Logit, same data set. Here we have in red the odds ratio. This is positive. So we expect a odds ratio that's bigger than 1. What we have, but when we add the 2 additional variables down at the bottom, we see that the odds ratios blow up from 1.2 to 2.2, 1.7 to 6.3, 2.7 to 38. Okay, why? Because these are not betas, these are betas over sigma. And sigma got a lot smaller. Okay, so when sigma gets smaller, beta over sigma goes up. In these cases, the odds ratios change dramatically. But the IE's incremental effect, ME's marginal effect, these again hold constant and are basically the same as from the linear probability model. 0.05, 0.1, and 0.2. The marginal effects are holding constant. The odds ratios are blowing up. I think we're about out of time, but well, we've got a few more minutes. Go ahead.
Sorry, really quick question then. I know we don't have a lot of time.
Yeah.
So why wouldn't you just use a linear probability model? I guess another way of rephrasing that is, when your probabilities are reasonably, in the middle, right, 20 to 80%, so to speak, a linear probability model is probably going to give you the same thing as a Logit model followed by marginal effects. So is there any advantage of using marginal effects over a linear probability model in those circumstances?
So partly it's a matter of religion. There are people for whom, if you have a binary outcome, this makes no sense. You cannot do this because you might get predicted probabilities that are negative. I mean, that often happens, or greater than 1, makes no sense theoretically. So you cannot do this. But if your goal is to estimate an average marginal effect, it is often the case, particularly when the underlying probability is somewhat in the middle, not at the extremes, that the marginal effects will be similar. Yeah. Okay, so there are also economists who have religion the other way, and you should always do linear probability model. You should never do Logit or Probit or any other linear binary outcome. I don't like either of those approaches. Partly it depends on the research question. Are you using it to calculate probabilities, or are you doing it to calculate marginal effects, or are you feeding it into something else in the model or do other calculations? Certainly, there are cases where what you're doing makes no sense if you calculate probabilities that are less than 0, greater than 1. So this probably is a bad idea. Overall marginal effects will usually be very similar, a little less likely if you have wide-ranging covariates and floor-ceiling effects, and then it's a little more difficult to match them up.
If Probit is subject to the same limitations as Logit as far as
Exactly the
scaling? Same thing. Okay.
For exactly the same reason. The only thing that would be different in this talk going Logit to Probit is that Probit has more complicated math because the things don't simplify in a nice way, and it assumes a normal distribution instead of a logistic distribution. They're from 20 feet, they're indistinguishable. Okay, so it's exactly the same problem. The math is a little dicier 15 slides ago. Okay, so odds ratio is not stable, marginal effects are stable. Next slide. So in conclusion, odds ratios are often reported, I think, without the proper discussion of what they're conditional on and this arbitrary scaling. You cannot compare odds ratios, and if you force yourself to always think of estimating beta over sigma, that'll help you remember that I don't know what sigma is, and will remind you that in many cases, it doesn't make sense to report odds ratios. So consider estimating marginal effects, risk differences, which are not sensitive to changes in sigma. I think that's it. Next slide. Yeah, then we're just into references. Okay, who has questions?
was excellent, thank you. So the public has a hard time understanding odds ratios and they require explanation.
Yep.
Marginal effects I find harder to explain still.
So, and I would say, like anything out risk ratio, risk difference, marginal effects, odds ratios, you always want to add additional information. What's the underlying probability? So underlying probability of catching COVID if you're unvaccinated is, I don't know, 10%, and getting vaccinated changes that from 10% down to 2%. So it's a marginal effect of 8 percentage points. Something along those lines helps provide the context and put it in terms of marginal effects. So perhaps I should have said the key thing is not just marginal effects and I'm done, but marginal effects combined with here's the base probability, or maybe the baseline probability is 82% of something, and then marginal effect around that.
Thank you.
Although in general probabilities are complicated. In college, I knew someone who was brilliant and eventually became a Rhodes Scholar, and she really didn't understand probabilities. It was a little odd.
One more. So
Yeah.
another way that sometimes you try to kind of get around the odds ratio issue is to use like a log binomial or even a Poisson regression. Where do you think that falls in sort of the model decision making given this issue? Or general issues of like interpretability and.
So let's say you estimate Poisson, then what do you do with that? So, I mean, nobody knows what a Poisson coefficient is on its own.
Mm-hmm.
So, you get some betas out of that. What do you do with that?
You exponentiate.
Sure. Yeah, and then, but then you get a marginal effect of some flavor. So you're going to end up back with a marginal effect, which makes sense. Yeah. And I will say, I have another whole talk on something quite different. I used to be much more negative about Poisson models, and I've come around to think they're actually much better, at least in other contexts. I haven't thought about them so much for binary outcomes, because at one level, Poisson models make no sense for a purely binary outcome because they're count models. So by definition, if you take them seriously, they're going to give you the probability not only of 0 and 1, but of 2, 3, 4, 5. So if you're of the religion that you cannot run a linear probability model because that goes outside 0, 1, then you would also be of the religion that this model with multiple gods, with multiple possible outcomes, 0, 1, 2, 3, 4, 5, should not be possible either. Again, I don't think that makes sense. I think Poisson can be very useful. It's what you do with the betas and how you frame the answer. But Poisson is remarkably flexible in the same way that OLS regression is just darn good at summarizing data.
I have one last question before I wrap up. Can you talk a little bit, just very briefly, about interaction terms and logistic regression models and how that's basically really dangerous because essentially
It's not dangerous, it's complicated. So I have a whole talk on that if you really want to dive into that. And again, it goes back.
We'll have you back.
And again, it goes back to if you understand interaction terms in ordinary least squares. So you have one variable, you have another variable, you interact them and include all three. You very likely understand exactly how to interpret everything in ordinary least squares. That intuition does not translate to nonlinear models. And one way to think of it is when you're calculating the effect of that interaction. So you have a treatment group, you have a control group, you have treatment times control. That's the interaction. That gives you the experimental effect. Treatment control in the post period. Implicitly, somewhere in your brain, you're taking a double derivative of an ordinary linear least squares regression, the right-hand side, you're taking a double derivative, everything falls out except the beta on the interaction term. When you take the double derivative of a logistic regression, the math does not simplify. It does not reduce down to beta. And that's, once again, intuition from linear OLS does not translate to intuition, appropriate intuition for a nonlinear model, and things break down and get interestingly complicated.
Topic for a future seminar. Thank you so much for coming.
Sure.
Glad to do it. Or maybe I'll invite you back to do the modeling expenditures, because that's the guy to work on, but yeah. It'd be good to actually something to do.
Clear about that?
You had mentioned.
Yeah.
Yeah.
So it's an outreach topic. Where are you guys? Okay.
We're really there. Today is our this moment where we're going to decide if we're back to business, I think. But we both are meeting with Lisa separately.
Those are just methods that a lot of people are using now.